My name is Efstathiadis. I am the technical director of the High Performance Computing Facility. Myself and Eric Peskin. Eric is the associate director of the High Performance Computing Facility. We run the facility. High Performance Computing is a service offered by the Center for Health Informatics and Bioinformatics. And today's talk will talk about, we'll start with an introduction to high performance computing. We'll talk about some of the applications in biomedical research. We'll continue with some of the architectural trends that are being used in high performance computing. And then I'll give you a quick tour of the HPC resources that are available locally. So high performance computing is a very important scientific tool. It is used to answer high impact, very challenging scientific and engineering questions. And in order to do that, high performance computing requires significant computing resources, such as supercomputers and powerful servers and clusters of servers and data storage and high bandwidth networks, and also algorithms and sophisticated software tools. High performance computing empowers what we call computational science, that is considered the third pillar of science. Traditionally, we have two pillars, the theory and the experiment. And we can study things theoretically when we know the theory. So even with on a piece of paper, we can solve equations. And we can solve equations analytically, of course, if the theory is known. If the theory is not that known, is not accurate, then we do experiments. We collect data, and we analyze the data, and we try to extract knowledge from the data. But even that sometimes doesn't work because experiments are sometimes too expensive, or they take too long, or they are too fast to collect any data, or they're too dangerous. So in these cases, there is a third option to do computational mathematical modeling. You can simulate something, then you can study something. So high-performance computing enables game-changing advances in life sciences. As a matter of fact, life sciences is the fastest growing area in high performance computing. So I'll give you some representative examples. Using fluid mechanics to study heart models. Using molecular dynamics to study protein folding, the process that a one-dimensional amino acid takes a three-dimensional form that's biologically active. Understanding HIV infection, simulating the protein that encapsulates the HIV virus, and understanding the process by which this protein disassembles, dissolves, gives us a lot of insight about HIV infection. Evaluating candidates for new drugs through the process of docking, studying docking of small molecules on proteins, or even studying docking of large molecules, proteins on proteins, that can give us a lot of information about drugs. Or assessing the risk of abdominal aortic aneurysm, the AAA rupture. In this study, researchers, they take CT, computed tomography scans of aneurysms. They build three-dimensional models, and then they run simulations taking into account various conditions like pressure and elasticity of material, and they try to come up with an assessment whether a specific an aneurysm and a AAA on a patient is about to rupture or not. And we learn wonderful things from that, such as what are the factors that affect the rupture of a abdominal aortic aneurysm. Is it the size? Is it the curvature? Is it the elasticity, et cetera? So this is very important work. These examples require significant computing resources. These are not simulations that you can do on a single server or a single processor. It requires many processors to require jobs that initiate many processes, and requires communication among these processes in order to carry out this type of calculations. I'll give you a more detailed example of a simulation that's done here at NYU by Boyce Griffith. What you see here is a 3D simulation of the fluid dynamics of the aortic heart valve. The method that's being used in this simulation is called the immersed boundary method, and it was introduced by Dr. Peskin, the father of Eric Peskin, down at the Quran Institute of Mathematical Sciences. In this model, so I'll try to play it again if it's a guess. What happens is, in addition to the fluid mechanics, the immersed boundary method takes into account the interactions of the fluid with the material, with the substance. So the heart valve, the aortic heart valve, is simulated as an immersed elastic boundary inside the incompressible fluid. And also the aortic root is treated as a semi-rigid elastic surface. So taking into account these interactions is very important because it leads to a realistic model for the aortic heart. And of course, again, this is another example of a very computationally intense simulation that you cannot do on a single computer. And it has great benefits studying this type of things. For example, by this simulation, we understand more about cardiovascular disease. We understand more how to treat cardiovascular disease, and we understand more how to design heart devices. So this is great research that can only be enabled by using high-performance computing. On the other end of the spectrum, these examples so far were very compute-intensive. There is data-intensive computing. This, for example, an example that is considered the best practices in calling single nucleotide polymorphism and small insertions and deletions using next-generation sequencing. So we produce the data, the raw data that comes out from DNA sequencers. We go through a phase that's called quality control, where we remove barcodes and we trim reads. And then we align the reads, the trimmed reads, to a reference genome, if such a reference genome exists. Then we go through a process of removing duplicates, which are basically machine artifacts, the result from PCR amplification of the sequencing process. Then we go through a process called the local realignment and base quality score calibration. During the realignment, what is done in areas where the quality score of the bases is low, this is usually towards the end of the reads, can fool the mappers. And they can call a series of intels instead of calling a series of SNPs instead of calling a small intel. So the approach here is that there is you do an alignment of a consensus of reads. So instead of aligning each read individually, you align a group of reads together, and this helps you do a better job. And finally, you call the SNPs. And at the end of this step, you end up with thousands of SNPs. And of course, this is the first phase. Later, after that, you need to select the relevant SNPs and indels, and you need to annotate. And there is a lot of work further downstream that Stuart Brown and the Sequence Informatics group do almost daily. So this is a very very data-intensive, because the output of next-generation sequencing instruments is millions or tens of millions of reads. So to do this type of analysis in a reasonable time frame, what you end up doing is something we call data parallel. So you take, you split the data into subsets, and you run the same pipeline in parallel, in pseudo-parallel. So these pipelines do not interact with each other, but you run them at the same time. And this way you shorten the time that it takes to analyze. In general, DNA sequencing, next-generation DNA sequencing, bioinformatics, and high-performance computing are very closely related. They are very tightly connected, and they work together to address this type of data-intensive problems. The challenges in next-generation DNA sequencing is that technologies change quite often. Every few months, we have a new sequencing technology that produces different types of data with different quality scores, different amounts of data per run. But as you can see in this embedded graph here, I don't know if you can read it, it shows the price per genome, the sequencing, how much it costs to sequencing a genome. And as you can see, when next generation sequencing was introduced, I'm not sure if you can see it very clearly up there, but the price dropped almost exponentially. So regardless of the technology, we're seeing high data throughput, all the technology high data throughput, and the cost quickly approaching the sequencing cost quickly approaching $1,000 per genome. So the sequencing is not so much the challenge. What is really the challenge is in bioinformatics. The challenge is really the analysis. That's where high-performance computing has most of its contribution. It takes a few days to sequence, to do a whole genome sequence, to sequence a whole genome, and it costs a few $1,000s. But really, to do the analysis, it may cost tens of thousands of dollars and takes weeks. And as we keep getting more data and more sequencing technologies come into play, bioinformaticians and the biologists, they change their interests. They can do all kinds of different things. So high-performance computing can help either by introducing new paradigms, for example, cloud or MapReduce, or introduce new computer architectures like graphics processing units, or new algorithms like the Barrows-Wheeler transformation that's used in aligning short DNA reads or reference-based compression. But really where we're heading into is moving into big data analytics. Data-intensive bioinformatics can help us with things like finding SNPs and structural variations and translocations and find association diseases, et cetera. But what really is needed here is some way to combine data from the omics, the genomics and the proteomics and the metabolomics, et cetera, with electronic health records and with insurance claims and other sources of data. And through some big data analytics, which is question mark what this could be, we can build a smarter healthcare system so we can treat disease better and do better interventions. So the big question is, how can we address that? How can we address big data analytics in biomedical informatics? We already have been doing some, and there are some technologies that are helping that way, such as machine learning or causal discovery or Bayesian networks and hypothesis-free approaches. And we know that this is possible because in the commercial world, this is already happening. We know that Google, for example, goes through petabytes of data on a daily basis from web logs and from web crawlers. And there is credit card fraud agencies that go through millions of credit card purchases, try to detect fraud. Or the Homeland Security Department goes through phone calls and through emails trying to identify threats. So out in the commercial world, there is already a lot being going on. And here in the biomedical area, things are trying to start. Here is an example. I'm not going to go through these two examples in great detail. These are examples that examples of studies that we did at the Center of Health Informatics and Bioinformatics. One is predicting osteoarthritis regression, severity, incidence, and pain. And basically what we see here, we have data coming from different sources. Then we have 12 different types of responses, 3 different classification methods used. The performance of each classifier was evaluated using the area under the ROC curve. And there was, the data was split 10 times, and we did 10-fold validation design. To do a study like that, we need to build 21.6 million models. And although each model does not take too much time to run, it depends on the size of the data, of course, but it takes, in typical cases, a few minutes, still is a lot of models. So to do this type of study in a reasonable amount of time, you really need powerful computing resources, high-performance computing. So I would like to introduce a couple of concepts before I end this introductory session. One is the campus cyber infrastructure concept. The campus cyber infrastructure is a local integrated environment that is set up to support research, to enhance the research capabilities, to empower collaboration, and of course to attract funding and talent. So it's not just powerful computing resources. It's also data sources like instruments and data sensors. It's also a powerful and secure and high bandwidth network. It's also service, and most importantly, is also training and education. So here is a schematic diagram of the components you expect to find in a campus cyber infrastructure. You have scientific instruments. There is a laboratory information management system that manages data, communicates with the researchers, and also there is biobanks and biorepositories. Data stored in a centralized high-performance computing data storage system that has direct access to the high-performance computing resource, like an HPC cluster. There is authentication and authorization schemes in place. There is, of course, visualization facilities, and of course, there are electronic health records. And everything is connected through a high bandwidth secure network. That should, though, allow collaboration you should allow us to exchange data with our collaborators. It should allow us to upload and download data from public archives. And of course, it should allow communication with public clouds and national cyber infrastructure. Now, the national cyber infrastructure is what supports world-class leadership shared systems. And it makes sure that these leadership systems that are not, of course, may not, of course, be available in a campus cyber infrastructure are accessible by researchers at various campuses. The national cyber infrastructure should enhance collaboration and across distances and across disciplines, and should make sure that data and software that was acquired at great expense is safe and is accessible by researchers. The national cyber infrastructure is what makes US globally competitive and what makes US the leader in science and technology. And of course, supported by the NSF, the National Science Foundation, the Office of Cyber Infrastructure. So this is the Branscomb Pyramid. It was introduced back in 1993. And basically, it was introduced to show the structure of our national cyber infrastructure. So what you see at the top, you see a few systems. These are world-class systems that only a few privileged users can have access to them and know how to use them. And then further down on the bigger base, you see several systems that are housed in supercomputing centers. And then you have more medium number of users being able to access and use them and do research with them. And then you get to the campus level, where you have large campus systems, shared resources by a large number of users. And then finally, you get to powerful lab workstations. Even more and more users can use them. So many will argue that this type of pyramid, this structure of the national cyber infrastructure has fundamentally changed for a number of reasons. One reason, for example, is cloud computing. The fact that individual users do not have to use any more local resources because they can just access cloud resources from public cloud vendors that have enormous computing capacity, and they can rent it out to users and pay for it on a per-use basis. Another reason is science gateways. Science gateways allow users to access through portals powerful resources and powerful data repositories. And science gateways are usually developed by communities. They have a nice GUI or a nice web interface and make it easy for the average researcher to have access to these powerful systems. And another reason is even world-class systems and systems that are being housed in supercomputing centers. They are now more user-friendly. Most of them nowadays run Linux, and most of the researchers are familiar with Linux, and they are familiar with the user environment, and so they can access them easier. But although some will argue that the Branscomb Pyramid is not valid anymore as a description of our national cyber infrastructure, still there are some components here that still hold true. For example, the base of the pyramid. In the base of the pyramid, we have not only the number of users, but also have education of users. And most of the education of users is not happening on the world-class system. It's happening local on the campus. Another reason is innovation discovery. Most of the innovations and discoveries are happening at the campus level. So having a strong campus infrastructure is essential to the national cyber infrastructure. So along these lines, a local HPC facility must not only support powerful computing resources, but must also advance collaboration, and must be able to initiate projects, and must provide education and outreach and training, and also experiment with new technologies and develop benchmarks and trials. So the local high-performance computing facility, again, is part of the Center for Health Informatics and Bioinformatics, and it is a full-service facility that provides, of course, software, expertise, services, access to powerful local computing resources, but also has another extensive list of services and things that are available to our research community. I'm going to move over to trends. I don't know if you have any questions about the introduction to high-performance computing. Any comments? No? OK. So everybody might be familiar with Moore's law. Moore's law basically states, it was phrased differently, but basically states that processor performance doubles every 18 months. And there are two reasons for that. One was that we kept increasing the transistor density because transistors, which are the basic elements of integrated circuits, they kept getting smaller and smaller. But also because we're able to get higher clock frequencies of those transistors. And we're able to clock them at higher rates. So more transistors clocked at higher rates led to higher performance. So we saw an exponential growth in single processor performance for over 40 years. And in 1971, we're back to 0.7 megahertz. And by 2001, we're up to 1.6 gigahertz. That was a factor of, I think, 10,000, so improvement over 40 years. One of the characteristics of this exponential growth was that as the computer manufacturers were building new computer architectures, they were maintaining compatibility with the previous versions. So application code that was written by developers could effortlessly run on the new version of the processor. So that way, the code and the application was getting faster. So that was working great for the software developers because it was seamless, it was effortless. The code, the hardware was getting faster, so the code was getting faster. That was great. However, around 2003, 2004, there was a break on the exponential growth of the frequency that were running single processors. By now, in 2013 or so, we should be up to 30 or 40 gigahertz processors, and clearly we don't have these fast processors. We are stuck around 3 point something gigahertz. The reason for that is basically power. Power goes as the clock frequency to the cube. So for example, if you double the frequency of a processor, then you need to dissipate 8 times the power. And this, of course, dissipation is in the form of heat. Not being able to deal with increased power and dissipated heat led to the stop in the exponential growth of the frequency. So the approach that was taken by computer manufacturers was what we call a horizontal growth. So instead of having one fast processor, we have multiple processing cores on the same chip, on the same piece of silicon. So we have more efficient cores that we can turn them into more efficient performance. That's great, but now the software developers are being challenged because the serial code will not run any faster no matter how many processing cores you have on your CPU. It will only use one core. It will run as fast as before. The only way to get more improvement out of multi-core chips is through parallel computing. And that's parallel computing enters the mainstream. And I say enter the mainstream because parallel computing was common in scientific and high-performance computing before 2003 and 2004. So this is a graph that shows the progress. Basically, the green line that shows that we're still improving the density of transistors on a CPU, but as you can see, the frequency, the clock frequency, and also the dissipated power has plateaued, has been stable. Parallel computing is not easy. Writing parallel code is not trivial. It takes a lot of effort. And there are hardware issues with that too. For example, accessing memory from multiple cores is a challenge. I chose to show you one of the laws called Amdahl's law that shows that to get performance out of 2 cores is not trivial. For example, if you have a code and you parallelize your code, this is the parallel portion, and you parallelize 50% of your code. So half of your application is parallel. No matter how many processors you run on, the maximum speed up you can get is 2. And even if you parallelize 95%, this is the green line. If you parallelize 95% of your code, even if you run on thousands of processors, this is the number of processing cores you run on, you get a max of about a speed up of 20. So basically, Amdahl's law says that even if you leave small portions of your code serial, you get a big performance hit, and you will never be able to take advantage of the scaling of the number of cores that you have on your CPUs. So, okay, so parallel computing parallel computing and parallel design code is very, very challenging. So in the 80s or 90s, the landscape of high performance computing was as follows. We had Cray, which is now known as Cray Research, building big supercomputers, and they were dominating basically the supercomputing market in the 80s and the 90s. We had Unix becoming the operating system that was dominating. And Intel, although was and still is one of the kings of microprocessors, had a hard time putting up a supercomputer. And actually the first, so to speak, successful supercomputer is the ASCII Red that they built in 1996. And this broke the power record of 1 megawatt of power. It was the first supercomputer to use that much power. And that was always Intel's weak point, the power on their processors. Now, on the other hand, what we start seeing is the development of HPC Linux clusters. And this is happening because it's happening around 1994 because it's easy. It's what they call supercomputing for the masses. It's easy to just take inexpensive commodity components of the self parts, interconnect them together with network switches, and use the software, it's called message passing interface, to make this cluster of nodes behave as single coherent computing entity. And this became very popular, and the operating system that was running and still running on HPC cluster is Linux. It became popular because there is a plethora of applications, and even if those applications were serial, you can still use the cluster to run your serial job. It was easily extensible. You can just add nodes and scale your cluster to hundreds of nodes. And HPC Linux clusters also support heterogeneous components. In a supercomputer, it's very monolithic. So if you were to use a supercomputer, usually most supercomputers, the type of nodes and the memory per node and the type of cores is very monolithic. It's very homogeneous. In HPC cluster, you can have nodes with different memory or different cards or different characteristics. And that was very convenient. But clusters have their weak points. And of course, the biggest one is power. Clusters are not power efficient. You cannot really take clusters and scale them big and build a huge supercomputer that's going to compete with the fastest supercomputers now available. Someone described it to me as you have a train that runs really fast, and that's your cluster, and then you're trying to make it run faster, and you try to put the wings on it. You cannot have a train fly just because you put the wings on it. So the only way that this can be done is by starting with low-power processors and make those low-power, smaller processors fly, and that's the way to build a big and powerful supercomputer. So this is one of the pictures of the first cluster, and as you can see, it's just components of the self. It's just computers, interconnected with a network switch. There is a separate node, could be the front-end node. I don't know exactly what this is, but could be the front-end node, could be some service node. And users would just log in on the front-end node and submit their jobs to the batch system. So this started happening around 1994. This is a picture of our own cluster. We used to have our own cluster here. We nicknamed it Asclepius. We lost it in 2012, Superstorm Sandy, but we're rebuilding it. So I'd like to take a small detour and tell you a little bit about a completely different subject, but I think it will help us understand how we build supercomputers these days. What I used to do previously, before I joined NYU, I used to work in physics in a field called quantum chromodynamics. Quantum chromodynamics is the theory of the strong force. It's this theory that describes the force between protons, and the theory that describes the force between the constituents of protons and neutrons, which are quarks. There are 6 different types of quarks, but the most common hadrons, the protons and the neutrons, are made up of only 3. The carrier of this force is the gluon. It's like the carrier of the electromagnetic force is the photon. The carrier of the strong force is gluon. What makes this theory, the QCD, the quantum chromodynamic theory, the theory of the strong interaction, really complicated is because the gluon, the carrier of the force, they can interact. So gluons can interact. Photons cannot interact, but gluons can interact. And moreover, gluons can interact with themselves. This makes the theory very complicated. And it gives you some weird characteristics. For example, when you have quarks very close to each other, they don't mind each other at all. They don't feel each other at all, which is completely opposite from what we know from the electromagnetic theory. When you have charges really close to each other, then the force among the charges is the greatest. In strong interactions, that's completely opposite. However, if you try to take the quarks apart and move quarks out of a proton, then that's when the force really gets enormous strong. That's why it's called a strong force. Now, so this very complicated theory called the quantum chromodynamics that describes the strong force is not easy to solve in some energy regions. What happens when it's very difficult to deal with such difficult equations, we end up discretizing the four-dimensional space and time. So what we're doing is we're calculating the quantum chromodynamics properties on discrete points called on the lattice. That's why this approach is called the lattice quantum chromodynamics. Now, the lattice quantum chromodynamics problems have some properties that make it easy to map onto a supercomputer. If we discretize the quantum chromodynamics equations, we get a very sparse matrix that only nearest neighbors communicate. So if we are to build a supercomputer, all we care about is nodes sitting next to communicating between nodes sitting next to each other. We don't worry too much about nodes far apart. So we don't need a very powerful and expensive switch to accommodate this type of nearest neighbor communication. Another characteristic is that we do need from time to time to do a collective operation. So we need to do from time to time an operation to collect all the numbers from every processor and do a global sum. For that, we design a separate network called the collective network. The different nodes communicate with each other with small messages. So what is important in that interconnects is the latency. It's the latency network that's important, not the bandwidth of the network, etc. I'm not going to carry on through all the characteristics of lattice QCD, but the lattice QCD has some characteristics that can be very easily mapped into a supercomputer. And what we did, actually, we started designing a supercomputer called QCD on chip. It's quantum chromodynamics on chip. And this effort was centered at Columbia University. And we gave great emphasis on improving the performance per watt ratio. So you wanted to get as many gigaflops out per watt and make this system very energy efficient. The supercomputer was built on IBM system on chip technology. IBM has a technology where all the major components, the network, the memory, the processors, the cache, everything is on a single chip. And this is called system on chip technology. The project started in 1999. It was completed in 2004. There was a water-cooled machine. Actually, we ended up building 3 machines. 2 of them were housed at Brookhaven National Laboratory, which is on Long Island, about 60 miles east from here. One of them belonged to the United States Department of Energy. The other one was funded with RIKEN, from RIKEN. RIKEN is the NSF office, so to speak, Japan's NSF office. And the third one was funded by UK, and it was built up in Edinburgh, in Scotland. So this is a picture of the team. This is me here. And that's the rest of the team that some of the people who designed, like Bob Mohini from Columbia University, and the rest of the team that put the machine together. It was a very challenging project. It was very challenging because we started with redesigning the IBM, the PowerPC chip. And we put the components that would make QCD calculations easier to do. Then IBM, who was, of course, involved, actually, IBM Yorktown Heights, which is about 40 or 50 miles north from here, decided to take this machine a step further. And they used similar technology to aim to build the first petaflop machine. A petaflop is a quadrillion calculations per second. And the mission for that machine is basically to do biomolecular. So it shows that features, characteristics of a problem that we're using in a different science domain, like in quantum chromodynamics, can now be used in the biomolecular simulations. And the aim was to address one of the grand challenge problems, which was protein folding. I'm not going to go into detail how challenging this is. Basically, to do about 100 milliseconds simulate 100 milliseconds of a medium-sized protein, it takes about 3 years of calculations on a petaflop machine. This is very challenging. So IBM built Blue Gene machines. This is a picture that I took of the Blue Gene machine that we built at Brookhaven. It was a very, very dense environment, extremely dense environment. This is how these are CPUs. This is the picture of the CPU. This is the whole node, actually. Everything is on a 14.5 by 5.5. The memory, the CPU, everything is there. And if you notice, there are no fans. Everything is air-cooled. There are no fans sitting on CPUs because the processor was chosen to be power efficient. Everything was air-cooled. The fastest Blue Gene that we know is called Sequoia. Is the third generation of Blue Gene. The first generation of Blue Gene was the Blue Gene L. The second was the Blue Gene P, and the third one is the Blue Gene Q. He's sitting in Lawrence Livermore National Lab in California. He has 1.5 million processing cores. It's 1.6 petabytes of RAM. And the sustained performance at 16.3 petaflops. It was the fastest machine in June of 2012. And on the top 500, and now it's the second fastest machine in November of 2000. In November 2012, top 500, which actually I'll tell you a few things. Top 500, you can see there's the list of the most powerful supercomputers. It's updated twice a year. Once during the supercomputing conference here in the US every November. And there is an international supercomputing conference in Germany, that's in June. So the top 500 list comes out twice a year. Once in November here in the US and once in June in Germany. And the way supercomputers are ranked is by running a benchmark called the LINPACK. It solves dense linear equations. There is a website that all the results are kept there. It's top500.org. And basically this graph is all the information there. The yellow line shows the 500th, the slowest of the 500 supercomputers. And the red line is the fastest supercomputer. And this is over time. So in 2012, this is the fastest supercomputer, the latest #1 in the top 500 list. And the blue line is just the sum. And as you see, supercomputing power grows very, very linearly. It's almost predictable what we're going to get. So this is a table. I don't know how clearly you can see it. Basically, in the top 5 machines, 3 of them are Blue Gene Qs. One of them, again, is the Sequoia, the picture that I saw you in Lawrence Livermore. The other one is an Argonne National Lab in Illinois, and the third one is in Jülich in Germany. I keep talking about petaflops, so I thought I should put a note here that flops means floating point operations per second. So doing 1 floating point operation per second is 1 flops. And usually that's what we assume as the computational capacity of humans. If a human takes a pocket calculator, we can do 1 floating point calculation per second. So a teraflop is 1 trillion calculations per second. And if a human can do 1 calculation per second, then it would take about 31,000 years to do the equivalent of 1 teraflops. And a petaflops, and this is where we are now. We are in petaflop supercomputers, can do 1 quadrillion calculations per second. So it would take a human about 31 million years to do the same number of calculations. So what a human could do in 31 million years, a petaflop machine can do in 1 second. So it's enormous computing power. The top supercomputer is a Cray. From Cray Research. It's housed at the Oak Ridge National Laboratory in Tennessee. It used to be further down in the ranking, but it got accelerated with NVIDIA GPUs, graphics processing units. And I would like to say a few things about graphics processing units because they become more and more popular. So traditionally, back in the 80s and 90s again, GPUs were just used on desktop computers to render graphics. to drive your monitor, your CRT monitor. But pushed by the gaming industry, GPUs became more and more powerful. For example, to render a picture like this, we have millions of pixels. And for every pixel, very difficult and sophisticated equations need to be solved to calculate lighting conditions, reflection of light, absorption of light, colors, etc. And this needs to be done many, many times per second. So as you can see, the power of GPUs, again, to render this type of sophisticated graphics and movement was growing fast. And scientists and engineers noticed that. They said, how about if we take these powerful processors and use them for general purpose computing to solve mathematical and engineering problems? So this is what gives, this is what lets GPUs, the general purpose GPUs. And basically, general purpose GPUs work in a hybrid system. You have the CPU that runs the serial part of the code. And when there is a matrix multiplication or a matrix multiplication, or whatever, a parallel component, it can be offloaded to the GPU. So what do we care about GPUs? Well, we care about GPUs for a number of reasons. First of all, they have very high performance. They have thousands of threads. You can run thousands of threads on a single GPU. The latest NVIDIA Tesla, it's called NVIDIA Tesla Kepler, has almost 2,500 cores. They're low power. It's about 500 megahertz, less than a gigahertz each core, but still it's a lot of them, so you can carry a lot of calculation. The double precision performance of this GPU card is 1.17 teraflops, which is a lot. It works very well. It can do asynchronous overlapping calculation between the GPU and the main CPU. It's low cost and power per flop. Of course, adding a card in your computer, you add power consumption, but given that you are getting back a lot of performance, the cost per gigaflop drops significantly. It's easily accessible because anyone can just buy, you can buy laptops with GPUs these days. And it's becoming easier and easier to program. The NVIDIA has this environment called CUDA that can enable programmers to just write high-level code, C, C++, and Fortran, and program those cores. But GPUs are not suitable for every type of problem. It requires some knowledge of hardware, and of course, it requires that code must be rewritten, must be re-engineered. You can't just take your own existing code and run it on a GPU. You need to actually rewrite it. GPUs are very popular in life sciences. We are seeing more and more of this. They are very popular in medical imaging, like we have computed tomography and MRI. We see a lot of protein similarity measures and docking being done with GPUs. There is computational chemistry. Some bioinformatics programs seem to be ported on GPUs, and there is MATLAB. So the latest version of NVIDIA Tesla, the Kepler K20, we have available on some of our nodes on our cluster. And the same Tesla NVIDIA processor, that GPU that was used on the fastest supercomputer in the world, on the Titan. It's the same exactly GPU. So before leaving this section, I'd just like to a couple of comments. As I said, the progress we make in supercomputers is very linear, and we can predict easily that we'll have the first exascale system in 2019. There are many, many challenges in building an exascale system. If you just take the petaflop system, you try to scale it, and scale, for example, the power that is needed to run the exascale system based on how much power is being used to run the petaflop system. We'll need hundreds of megawatts. And that's not going to happen because we're going to need a power plant just to run such a system. So the challenge here of the committees that are trying to design such, and the architects trying to design such a system is to have an improvement factor of 10 in performance. And also, by 2015 or so, all 500 systems will have the top 500 list, will be over a petaflop. So there will be an abundance of supercomputers, an abundance of parallel architecture will be available, will be accessible to many of us, to do research. And we should learn how to program in parallel computing and GPUs to be able to take advantage of all this computing capacity that will be available. And another comment I want to make is that soon Moore's law is going to end. It's not going to last forever. We are, just because we use more cores doesn't necessarily mean that we are done with we have dealt with the power problem. The power density, and this is what's being plotted here, is watts per unit of surface. It keeps increasing. And if we keep going in this graph, soon we'll reach the power density of the nuclear reactor. And if we keep going, we'll reach the power density of the sun's surface. So it's not going to happen. And clearly, sometime in the future, we need to find other ways of doing computing and move away from silicon. And there are a few efforts out there, and one of them is quantum computing. And there is DNA computing, and there is optical computing, and no one knows which of these technologies will prevail, but one of them has to, because otherwise Moore's law will end. If you're interested in this stuff, there are a few very interesting references, especially the fourth paradigm, doing data-intensive scientific discovery is a very good book, and there is computing performance, game over or next level is also very interesting. You want to read more about these technologies. And also there is, I just found out about this a few days ago, there is an international summer workshop, international summer school on high-performance computing. This is happening downtown NYU this coming June. And there is funding available for graduate students and postdocs and faculty. The deadline, it says here, is March 18th, but I spoke to the people who organize, and they're willing to wait a few more days if people from NYU, from the School of Medicine, would like to apply. So if you are interested in attending the school and learning more about how to program multi-cores or GPUs or learn about visualization, let me know. The person who will deliver the keynote is Ed Sedell. You may have not heard of him, but he used to be the NSF director of the Office of Cyber Infrastructure, and now he's working at the Skolkovo Institute in Moscow, in Russia. If you guys are interested, if any of you is interested, let me know, and we'll do that. So before we end, I would like to spend a few minutes talking about the local available resources. So we rebuild our cluster, or we're in the process of rebuilding, and Eric is spending a lot of time on configuring the cluster. We nicknamed the new cluster Phoenix. It's a state-of-the-art cluster. It's a very powerful cluster. We custom designed it, basically. We designed the networks, and we made sure that the components we chose are power and cost efficient. We have 2 head nodes, and these are the nodes where the users log in to edit files, compile their codes, submit jobs, and do the day-to-day tasks. We have 64 compute nodes. These are the worker nodes. These are the nodes that actually execute the jobs, run the jobs. 5 of those 5 additional nodes, other than just being same as a regular compute node, but they also have the latest NVIDIA, Kepler, Tesla, K20 cards. We have 1 high memory node that has 32 cores. It has 1 terabyte of memory. And all these nodes are interconnected with carefully chosen high bandwidth networks. There is a 10 gigabit network that is used for message passing, just for communications between the processes that run on the cluster. There is a data network that is separate from the rest of the networks. It's just being used for I/O between the cluster and our centralized data storage. And there are a couple of 1 gigabit networks that are used for administration and management. So we're trying to separate all the overhead of administration and management from the message passing and from the I/O operations. So the total count of cores, if I counted correctly, is about 1,170 processing cores. We have around 12.5 thousand GPU cores. We have a total of 10 terabytes of RAM, and an estimated performance about 28 teraflops. So it's a powerful cluster. It's local, and it's easily accessible. This is a schematic diagram that I put together. It's basically the same description that I was describing in the previous slide. So we have the head nodes. The head nodes are connected to the enterprise, to the campus network. This is how the users log in and access the head nodes. And then these are the 64 compute nodes with 5 nodes equipped with GPU accelerators. And there is also the high memory nodes. And there are separate networks, one for the I/O, for the data that is accessing the Isilon, our data storage. There is the message passing network, and there are the administration networks. The user environment, we plan to organize a series of tutorials on how to access the cluster, how to use the nodes, how to submit jobs, etc. But this is just one slide. We're running Linux, CentOS. We connect to the head node via SSH. SSH standard is de facto, is based on a two-factor secure authentication. It's based on what you know, which is a passphrase, equivalent of a password, and also what you have, which is a private key. Standard tools used to copy data, move your data from your laptop or your desktop to the cluster front-end node. And once the users log in, they will have access to home directories and the group share data. And there are also disks that are available on each worker node. So if there are jobs that do intensive I/O, sometimes it would be beneficial to the jobs to stage the data on the worker node where the code actually runs, and then stage the results out. And job management is done with a batch system. It's called the Sun Grid Engine. It's one of the popular batch systems and easy to use, and that's what we used to use in our previous cluster, and we're just going to use the same thing on the new cluster. As for software, we're just going to have the standard system software that users will be able to edit files and submit jobs and do message passing and do version control and transfer data. There is a ton of biomedical software. There's a lot of bioinformatics software. And there are some scientific libraries, such as MATLAB, R, etc. And if there is, Research IT basically manages licensed software. So if there is a package that you need and it's licensed, you may inquire with the Research IT whether they could fund it so we can deploy it on the cluster. We have a petabyte of data storage. It's raw, so meaning that if you just take the disks and you count how much capacity this disk has and you multiply by the number of disks, you get about 1 petabyte. This is our primary storage, and this is where all the data from instruments like the DNA sequencers and scanners and microscopes end up. It's directly attached to the cluster nodes with a private dedicated network. And that's where we store, that's where we have home directories and group share data, and that's where we also store snapshots of the file system. We have 2 clusters, actually, so our data storage is split into 2. One is the primary that is located in the Karlstad data center, and the other one is the backup, is in Smilo. It's in this building, I think a couple of floors down from here where we are now. In addition to the primary data storage and the mirror, we do have cheaper systems that we plan to use to archive data. So data that has been analyzed and researchers do not plan to touch for years, we move them over to tier 2. We plan to move them over to tier 2 and then mirror the 2 systems. These systems exist, and one of the archived tier 2 systems is sitting in the Karlstad data center in New Jersey, and the other one is sitting on the Translational Research Building. That's where our headquarters are located. And we're looking into getting into a tier 3, possibly, Glacier type file system where we just put data there and we keep them for years. One of the great advantages of our setup is that we're trying to make it very efficient. So we're trying to store data on our Isilon cluster and make this data directly accessible from the HPC cluster. So we don't need to make extra copies of data, and we don't need to flood the network with moving data around because we need data to be accessed by some services, or because we need data to be accessed by the cluster, or needs to be accessed by the instrument. So the data comes out from various instruments, local instruments, like, again, microscopes and slide scanners and RNAi interferometry instruments and sequencers, and they end up into the primary data storage, and it's immediately available for analysis. Another source of data is external public archives. And another source of data is simulation. So we run simulations, mathematical models on the cluster that generate more data, and everything goes into one place. And this is a graph of their data storage. The blue line is our primary data storage, which is about 580 terabytes. The green line is the sum of the primary and the backup, and it's about 1 petabyte of storage. And the red line is the actual storage. So we monitor how much storage we have. And this is data, again, that comes out of instruments, local instruments, simulations, and public archives. And we are storing about, our rate is about 10 terabytes a month. And this is a picture, a physical picture of the place in the Karlstad data center. The cluster is in an area called IDC 6. There is a cage that's been designated for research and education. The cluster, the HPC cluster, along with the data storage, takes up 7 racks, about 40 kilowatts of power, give or take. And all the networking equipment and support for networks provided by the medical center IT. And the electrical power, space, cooling is also managed by the medical center IT. A few things I just want to say. I think I spoke about the facility before, so I'm just going to say that I'm the technical director, and Eric Peskin is the associate director. We are located in the Translation and Research Building on the 7th floor. The shared computing resources are located in Karlstad, New Jersey. We have emails, and we have problem tracking system that actually the problem tracking system was we lost it in Sunday. It's being rebuilt. But the best way, I think, to access to contact us right now is hpc_admins@nyumc.org. We have a lot of resources on our web pages, and we're planning a series of tutorials. We're trying to organize these hands-on 2-hour tutorials with the Sequencing Informatics group. So we did a couple of test runs of the tutorials for the first 2, but we're planning to have a series of tutorials. Our goal is to do all of them start in April and do one of them every week and do all 5 of them. So we'd like to stop here. Thank you very much. And if you have any questions, please let me know. Thank you. No? Yeah.
With outside collaborators, if you want to share data with them or resources?
Well, if they want to share, if outside collaborators need to share resources, for example, run jobs on the cluster, they will have to log in on the cluster, which means they will, right now the situation is they have to get a VPN access. So they need to apply for a Kerberos ID, they need to be sponsored for a Kerberos ID. Once they get it, they have to enable their Kerberos ID for VPN access. Once they enable the VPN access, we have to ask MCIT to let them specifically SSH to the front-end node of the cluster. And after all that happens, they will be able to access the. It's not. It's complicated, but it works. Yes, it used to work with our previous cluster. They used to work with.
It was fine. It wasn't that complicated.
Yes. But once you get all these things in place, then it works fine. I mean, just VPN, USSH the front-end node. Once all the permissions are replaced, it works. For sharing data, it's a little bit different because you don't really need to log in on the node to access the data. We used to have a web page that was available externally. So people would assign, Eric would assign to those external collaborators a username and a password. They would log in on the web page and would download data from there. Now we need to reestablish that. It hasn't been established yet. Again, Eric is very busy configuring the cluster, but our plan is to reestablish that and have that access. There are better ways to share data than downloading data off a web page. Large international collaborations, they can do it using different methods. Globus, for example, is a software that's being used to share big amounts of data. There is also professional versions of, well, not professional version of Globus, but professional packages called Aspera. It's also used to share data. So there are solutions out there, and we haven't been able to deploy much of it because there needs to be firewall conduits for this software, these types to work, and we don't have that in place. So we're trying to find workarounds, and a workaround is, for example, uploading the data on the Amazon cloud, and have the collaborators get them from there. And that's one solution. Or trying to pull data in rather than rather than initiating from inside to outside. Actually, instead of initiating outside to inside connections, we try to initiate connections from inside, and usually outgoing connections are most of the time open. So it's tricky though. I mean, it's hard. It's really hard to build a research environment where you do research on top of a business environment, right? So there are firewalls in place, and there are other things that. But so far we managed one way or the other. Anything else? Okay. Thank you very much. Thank you.